Okay, vaporization and vapor pressure. So we're going to talk about the transition between a liquid and a gas. So here we have an illustration of a beaker of water. So these water molecules are in constant motion. They're moving around, and some of them are going to come towards the surface. And we have an average kinetic energy, which is related to the temperature, but it's an average. Some of the molecules are moving faster, some are moving slower. If you get a fast-moving molecule that it's headed towards the surface, it may have enough kinetic energy that it can break loose and get into the gas state. It's essentially escaped, right? Now it's out here and it's free. Gases travel in straight lines until they run into something. So in an open beaker, that water molecule is probably gone. It's probably not coming back. It's just going to take off until it runs into something. It'll bounce off and just keep going. If you put a lid on this, though, the water molecules that get into the gas state are going to hit the lid and bounce and head back towards the water. And like this one right here, heading towards the water, when it hits the surface of the water, it's going to get stuck again. Right? This is kind of an interesting quote describing water molecules. It's a wild dance floor there at the molecular level. So it's kind of like a mosh pit. There's a lot of movement going on there. So these two terms we need to understand. Vaporization is going from a liquid to a gas. Condensation is the opposite, going from a gas to a liquid. So average kinetic energy is related to temperature. So we see that increasing the temperature increases the average kinetic energy. So here we have the blue line representing distribution of thermal energy at a lower temperature, and this at a higher temperature. So there's an average, right? But it's a distribution. So there are some particles that have very small energy, and there are others that have very large energy. So we look at this line here being the minimum kinetic energy that's needed to escape from the liquid. So even at a low temperature, some of the molecules have enough energy to escape. But if we increase the temperature, then more of them have enough energy to escape. So at higher temperatures, vaporization occurs more quickly. So think about which will get dry faster. A damp towel that's just sitting on a chair, actually it's more likely to be on the floor, right? Damp towel on the floor, or damp towel in the clothes dryer turned on with the heat. Which one dries faster? The one in the dryer. That was not a trick question. Maybe that's what you guys thought. Not a trick question. Why do we stick things in the dryer and heat them? Because it makes them dry faster, right? Because it speeds up the rate of evaporation. More of the particles have enough energy to get into the gas state, and so the thing will dry faster. So I have to tell you about my red Rover analogy. You guys old enough that you know the game Red Rover? Yeah. They don't let kids play that anymore at school. They can't even play tag. It's just so sad. So if you're not familiar with Red Rover, the way Red Rover works is you get two groups of kids on opposite sides of a field or an open area, and they hold hands in a line, right? And then somebody on one team says, Red Rover, send Sally right over, right? And so Sally on the other team lets go of the people she's holding on to, and she runs towards your line, and she's trying to break through, right? So she's going to go right where you're holding hands with the next person, and she's running really fast, and she's going to try to break through. And you're supposed to hold on tight and not let her through. You can see why maybe school administrators would not want this to be played, because, people could get hurt, a wrist could get broken. Nobody's going to put an eye out, though. But you could break your arm or something. So I see evaporation as being like a game of Red Rover. So you have these water molecules at the surface that are holding hands. And the holding hands is that intermolecular force of attraction between them. The water molecules down here, if they happen to be going in the direction of the surface, that's Sally running towards the line. If she's running fast enough, she can break through. If she's just strolling along, there's no way she's going to break through. She's going to get bounced back. She's going to have to go back where she came from, right? So the strength of the intermolecular forces affects how many of those molecules have enough energy to get out, right? So if you have strong intermolecular forces, it's harder to evaporate the water or the whatever it is. If you have weak intermolecular forces, it's easier to vaporize. And then temperature plays a part, because you increase the temperature, you're increasing the speed at which these guys are running. And so at a higher temperature, more of them will be able to escape. Any questions? So another way you can increase the rate of vaporization is to increase the surface area of the liquid. Because only molecules that head towards the surface can possibly escape. Right? If we go back to this beaker, if you've got molecules headed towards the side of the beaker, they can't escape, they can't vaporize. It has to be towards the surface. If you increase the surface area, now you have a lot more molecules that are headed towards the surface, and so they can escape. So increasing the surface area would be like, taking a glass of water, maybe take 2 identical glasses of water, leave one on the counter, spill the other one on the floor. What does water do when you spill it on the floor? It spreads out, right? My cats did this the other night. They knocked a cup off of the bathroom counter, and I walked through in the middle of the night in my socks, and I stepped in it. Thankfully, it was water and not pee, because that's usually what's on the floor if there's liquid. But it was just water. And I thought about it, and I'm like, it's the middle of the night. I don't want to clean that up. It'll evaporate, right? Sure enough, by the morning, it was all gone. It evaporated. If the cup had stayed on the counter, most of it would still be there, right? Because when it gets spread out over a large surface area, it will evaporate more quickly. Any questions about that? So we have 2 terms. These are qualitative terms, volatile and non-volatile. Volatile just means a liquid that vaporizes easily. Non-volatile is a liquid that does not vaporize easily. And so they are, relative terms. So alcohol is volatile. If you go get an immunization, they take an alcohol wipe and they wipe your skin to, clean it and sterilize it. And it evaporates very quickly, right? If you were to take a cotton ball with vegetable oil on it and rub it on your skin, you're going to be waiting a long, long time. Vegetable oil does not evaporate at room temperature. It just doesn't. It's non-volatile. Okay, so if that beaker of water was thermally insulated, meaning we're not allowing any heat energy to come in or go out through the sides of the bottom of the beaker, what's going to happen to the temperature of the water that's left in the beaker as the molecules evaporate? Well, let's look at this. Which molecules are the ones that are leaving? The low energy ones or the high energy ones? The high energy ones. The high energy ones are leaving. So if the high energy ones leave, what does that do to the average kinetic energy of what's left behind? It goes down, right? So as the liquid evaporates, the temperature of the remaining liquid goes down. So this is why in the Central Valley, you can get sweaty any time of the year, right? Here we've got this guy running, and you can imagine he's probably sweating pretty good. Why do we sweat? Because it cools our body. So your body sweats, puts moisture on your skin, A breeze comes, the moisture evaporates, and it takes away energy, thermal energy, so it cools you. It's also the principle behind a swamp cooler, an evaporative cooler. You got a pad, one of those weird-looking pads, and it runs water through there and blows air. So as the water evaporates, it cools. So evaporation is an endothermic process. Condensation, the opposite, is going to be an exothermic process. So condensation is going from a gas to a liquid. So I think most of us have experienced not necessarily a steam burn, but at least a sense of discomfort passing your hand over a pot of boiling water, right? You go to put the spaghetti in and you're like, ooh, that's really hot. Get my hand out of there. Because as the steam comes up, that's water in the gas state, and hits your skin, it's cooler, and it begins to condense, it releases a lot of energy to your skin. So steam can cause really, really bad burns. Vaporization and condensation are a big part of our climate. If we compare Fresno and San Francisco, I mean, we're roughly the same distance from the equator, so it's not that we're at different latitudes or anything. Here's average high temperature in Fresno, and this is July, years 71 through 2000. So average high in Fresno in July, 96.6. Average high in San Francisco, 68.2. Right? I used to live in the Bay Area. It's very, very different. The low, 66 in Fresno, 54 in San Francisco. And I think what's more striking than just the actual high and low is that the difference between the high and low. So in Fresno, the average difference between the high of the day and the low is 30 degrees, whereas in San Francisco, it's less than 14. The temperature just does not change very much there. Condensation and evaporation is the reason. San Francisco is surrounded on three sides by a large body of water, the ocean and the San Francisco Bay. And what happens is the sun comes down. The sun is what brings us energy, heat during the day. It hits the water, and the water begins to warm up. The water begins to evaporate, and so that absorbs some of the energy from the sun. Sun goes down, source of heat is gone. The water in the air begins to condense back into the bay. As it condenses, it releases energy. And so San Francisco does not get as hot during the day or as cold during the night. Around here, there's not much water, right? So our temperatures vary a great deal. Any questions? Well, I have a question. Why will my thing not change slides? Because it's out to get me. The universe is out to get me. It's a conspiracy. Pause.